Let's talk about a question that, it probably haunts every single software developer. You write a piece of code and it works perfectly today. But is it still going to be correct a year from now after dozens of other people have made changes to it? Let's figure out how we can make sure the answer to that is always yes.
Right. This is the fundamental problem we're all dealing with in software. Code is never static, is it? It's always evolving, and every single time it evolves, there's a risk that something that used to work perfectly suddenly breaks, and usually in some subtle, totally unexpected way.
So, to make this really concrete, we're going to follow the life of a pretty simple program, one you've probably written a bunch of times yourself. All it does is count how many times each word appears. You can add words, you can remove them, and you can check the count for any word you want. Super simple.
So how do we know it works? Well, the first thing we all do is pretty straightforward. We write a little main function, we throw in a few words, remove a couple, and then just print everything to the screen. And we look at it and go, hey, looks good, right? Foo is there once, pause is gone, it's perfect. And, this feels like enough, doesn't it? We just saw with our own eyes that the code works. So what's the problem? And this really gets to the heart of it. What is the actual point of writing tests? Because if it's just to prove the code you just wrote works, well, we already did that.
That question right there brings us to our first big idea. See, the real purpose of tests isn't about checking the code you wrote 5 minutes ago. It's all about building a safety net for the future, for you and for every single person who's ever going to touch this code. So here's the crucial takeaway. Automated tests are basically an insurance policy. Their number one job is to make sure that when you, or maybe someone else, comes along and changes this code 6 months from now, or heck, 6 years from now, you don't accidentally break something. They're your guard against future mistakes. And this safety net, it has a whole bunch of different layers. You've got unit tests, which we developers use to check the tiniest little pieces of our code all by themselves. Then you have things like acceptance tests, which make sure the software actually does what the client asked for. And you even have performance tests, which are kind of like a stopwatch, making sure your code doesn't get slower over time. They all have a different job, but they all work together to keep you safe.
Okay, so we know why we need that safety net. But what makes a good one? A really great test doesn't just tell you something's broken. It tells you exactly what's broken. It's the difference between getting a vague, cryptic clue and just being handed the answer. Now, a good first step up from just looking at the output is to automate the check. We can toss in a simple assert statement. This basically tells the program, hey, I expect this to be true. If it's not, just crash. It's a simple check that'll run every single time. But here's the catch. When that assert fails, the message you get is, well, it's not super helpful. It might just say assertion failed and give you a line number. It tells you that something went wrong, but it gives you absolutely no clue as to what or why.
And this is the key insight. A vague failure like that forces you to put on your detective hat. You got to stop what you're doing, fire up a debugger, and start manually stepping through the code just to figure out what the values were and why they didn't match. It is a massive waste of time. This is where we seriously level up our game. On the left, with a simple assert, you get assertion failed. That's it. That's all the help you get. But just look at the right. A modern testing framework is like having a helpful colleague. It doesn't just say, you're wrong. It shows you why. It says, you required h.size to be 3, but I checked and the actual value was 2. The difference is just night and day. So that's the whole ballgame right there. A good test failure is a gift. It hands you everything you need on a silver platter, exactly what condition failed, what you expected to see, and what you actually got. There's no detective work needed, just a straight path to fixing the bug. Okay, so a good framework gives us some serious superpowers. But even with the best tools in the world, it's still surprisingly easy to build a safety net that's full of holes. So let's look at a couple of common traps that can make our tests fragile and, honestly, a pain to deal with. All right, here's a classic situation. You're trying to make your code faster, so you decide to change an internal implementation detail. You switch from a sorted map to an unsorted hash map. Now, the public behavior of the code should be exactly the same, but the internal order of the elements is going to change. So our first test was brittle. It was checking that the words came out in a specific alphabetical order, which was just an accidental side effect of using stdmap. The moment we switched to unordered map, the test broke, even though the code was still 100% correct. A robust test, on the other hand, only cares about the content. It checks that the right words and counts are there, and it doesn't care one bit about what order they're in. Now for the big one, a question that has confused developers for literally decades. You've got some really complex, important logic, but it's all tucked away inside a private helper function. How in the world are you supposed to test that directly? The common advice you hear is, oh, you don't test private functions, which, let's be honest, is not helpful at all. The truly elegant solution isn't to try and hack into the class to test it. Instead, you just do a simple refactor. You pull that complex logic out into its own separate public utility. Now you can test that utility directly as much as you want in total isolation. And the original class gets simpler. It just calls the utility it needs. It's a win-win. And that idea, refactoring our code just to make it easier to test, that leads us to our final and maybe most powerful insight. What if the difficulty of writing a test isn't a problem with the test at all, but is actually a message from your code? Have you ever sat down to write a test for some piece of code and just found it incredibly painful? Like you have to create a dozen different mock objects, fake out all these complex dependencies, and the test itself just explodes into this 100-line monster. That struggle, that's not a sign that you're bad at testing. It's a sign. It's your code, literally trying to talk to you. It's yelling, I'm too complicated. I'm trying to do way too many things. My responsibilities are all tangled up. That feeling of struggling to rate a test is a huge, blinking neon sign that the design of the code itself could probably be a lot simpler. So, let's wrap this up with the most important takeaways. First, start thinking of your tests as living documentation that can never go out of date. Second, keep each test super simple and focused. But the most important one is this: never, ever tolerate a flaky test. One that fails randomly. A flaky test is absolute poison to a project because it teaches your whole team to just ignore test failures. If you find one, you either fix it immediately or you delete it, period. At the end of the day, writing good tests is really an act of kindness. It's kindness to your future self, and it's kindness to every other developer who's ever going to work on this project. You're building that safety net that lets the code grow and change with confidence for years and years to come. So the next time you're struggling to write a test, don't get frustrated. Just stop and listen. Your code might be trying to tell you something really important about its own design. And learning to listen to that feedback, well, that's what separates the good programmers from the truly great ones.